Today we shall study about semiconductor diode. A semiconductor diode is basically a PN junction with metallic conducts provided at the ends for the application of an external voltage. It is a two-terminal device. A PN junction diode is symbolically representing in figure B. The direction of arrow indicates the conventional direction of current. When the diode is under forward bias, the equilibrium barrier potential can be altered by applying an external voltage V across the diode. The situation of PN junction diode under equilibrium without bias is shown in figure A and B. PN junction under forward bias, when an external voltage V is applied across a semiconductor diode such that P side is connected to the positive terminal of the battery and N side to the negative terminal as shown in figure A, it is said to be forward biased. The applied voltage mostly drops across the depletion region and the voltage drop across the P side. And N side of the junction is negligible. This is because the resistance of the depletion region, A region, where there are no charges, is very high compared to the resistance of N side and P side. The direction of the applied voltage is opposite to that built-in potential VO. As a result, the depletion region bar layer W and the depletion layer width decreases and the barrier height is reduced. The effective barrier height under forward bias is VO minus V. If the applied voltage is small, the barrier potential will be reduced only slightly below the equilibrium value and only a small number of carriers in the material, those what happen to be in the uppermost energy levels will possess enough energy to cross the junction, so the current will be small. If we increase the applied voltage significantly, the barrier height will be reduced and more number of carriers will have the required energy, thus the current increases. Due to the applied voltage, electrons from N side cross the depletion region and reach P side where there are minority carriers. Similarly, holes from P side cross the junction and reach the N side where there are minority carriers. This process under forward bias is known as minority carriers injection. At the junction boundary, on each side, the minority carrier concentration increases significantly compared to the location far from the junction. Due to this concentration gradient, the injected electrons on P side diffuse from the junction edge of the P side to the other end of the P side. Likewise, the injected holes on N side diffuse from the injection edge of N side to the other end of N side. This motion of charge carriers on either side gives rise to current, the total diode forward current due to electron diffusion. The magnitude of this current is usually in milliampere. PN junction diode under reverse bias, when external voltage is applied across the diode such that reside is positive and P side is negative, it is said to be reversed by figure 1a. The applied voltage mostly drops across the depletion region The direction of the applied voltage is same as the direction of barrier potential. As a result, the barrier height increases and the depletion region widens due to the change in electric field. The effective barrier height under reverse bias is V0 plus V. In figure 1b, this suppresses the flow of electron from N to P and holes from P to N. Thus, diffusion current decreases enormously compared to the diode under forward bias. The electric field direction of a junction is such that if electrons on P side or holes on N side in their random motion come close to the junction, they will be swept to its majority zone. This drift of carriers gives rise to the current. The drift current is of the order of a few microampere. This is quite low because it is due to the motion of carriers from their minority side to their majority side across the junction. The drift current is also there under forward bias, but it is negligible mu A when compared with current due to injected carriers, which is usually in milliampere. The diode reverse current is not very much dependent on the applied voltage. Even a small voltage is sufficient to shift the minority carriers from one side of the junction to the other side of the junction. The current is not limited by the magnitude of the applied voltage, but is limited due to the concentration of the minority carriers on either side of the junction. The current under reverse bias is essentially voltage known as breakdown voltage, VBC. When V over VBC, the diode reverse current increases sharply. Even a slight increase in the bias voltage causes large charge in the current. If the reverse current is not limited by an external circuit blow, the rated value specified by the manufacturer, the PN junction will get destroyed. Once it exceeds the rated value, the diode gets destroyed due to overheating. This can happen even for the diode under forward bias if the forward current exceeds the rated value. The secret arrangement for studying the VI characteristic of a diode, it means the variation of current as a function of applied voltage, are shown in figure 1a, b, figure 2a, b. The battery is connected. The battery is connected to the diode through a potentiometer or rheostat so that the applied voltage to the diode can be changed. For different values of voltage, the value of current is noted. A graph between V and I is obtained as in figure C. Note that in forward bias measurement we use a milliammeter since the expected current is large, while a micrometer is used in the reverse bias to measure the current. We can see in figure 2C that in forward bias the current first increases very slowly, almost negligibly. Still, the voltage across the diode crosses a certain value. After the characteristic voltage, the diode current increases exponentially. Even for every small increase in the diode bias voltage, this voltage is called the threshold voltage. Threshold voltage or cut-in voltage. Minus 0.2 volt for germanium and for germanium diode and minus 0.7 volt for silicon diode. For diode in reverse bias, a small current microampere is called reverse saturation current, and dynamic resistance बराबर RD बराबर डेल्टा V बटा डेल्टा I.